in quantitative big imaging. And so this lecture will actually combine some of the things that didn't fit into the other lectures, so this sort of texture analysis, but we'll have that at the end. And so for now, what we'll start off with is this many objects and distributions. And so if we look at kind of the outline of what we had, that last week and the week before, we really covered how do you analyze single objects and more complicated objects. And this is really trying to put that all together into what can you actually do when you have a large number of objects. And so very frequently when you're dealing with cells like neurons, it's very interesting to analyze one or two of these cells and see how they look and what their shape is. But it's much more interesting if you can actually start to analyze a large number of these different objects and see how they're related to each other and how they're positioned. Similarly, from projects I've worked on myself, when you're looking at bone and the osteocyte lacuna inside of them, knowing how they're distributed can tell you a lot about what their functions might be. And so if you look at the individual cells, they're not always particularly interesting, but when you look at the patterns that they form, you can tell a lot about the sample that they're inside. Then next week, there's no lecture because of Easter, I guess, although that seems like it should have been this week. And then the week after, there's the statistics and reproducibility. And so that's about putting all these aspects together so that we can have sort of a meaningful output from all of this different analysis. Because ultimately, all of these tools we're developing are meant for making scientific studies, and you want to be able to show that what you've done with your data is meaningful, and whether or not there are potentially differences in your groups and what sort of tools are available for that. Then we'll get on to dynamic experiments and sort of the more interesting advanced lectures. So the literature is an extension of sort of what we've covered before, but there's a number of new papers on here, particularly Voronoi tessellations, nearest neighbor and self-avoiding ideas, and then this sort of alignment and distribution tensor. So we've got a number of things you can look at if you're interested in getting more information about those topics. You should be able to scroll here as well. And then finally, the two-point correlation function, which we also briefly mentioned last time. So if we look at what we previously covered, we sort of had all of these different tools that we made to get from our original images to some kind of shape. And so we've segmented the features out, we've gotten rid of noise, we've figured out what's actually interesting, we've measured some positions, some shapes, and now the question is really what can we do with this? And so the outline we have for this today is sort of what are we trying to quantify inside of these objects. And so one of the things that's very interesting to look at is like the local environment. And so when you're looking at cells, what is around them, what things are close to them, what things are further away. That also fits very well into neighbors. So how many different objects are touching your current object or potentially in contact with it. And then we'll cover sort of the mathematical tools which enable us to do these kinds of analysis. And so that would be the Voronoi tessellation, which is used in a large number of different areas, not just image analysis, and then distribution tensor. And so both of these tools are quite useful for a lot of the analyses that we'll cover and good tools to be generally aware of. The global environment aspects will then cover sort of beyond sort of the immediate vicinity of one object that you're looking at. And what the global environment focuses on are things like alignment. And so, as we mentioned, I think in the very first lecture, when you have a bunch of cells or a bunch of fibers that are oriented in a specific direction, it's very easy to measure their orientation. You can measure an angle, you can measure it in spherical coordinates, you can measure sort of an x and y or whatever else you might want to do. It's then much more different to come up with a metric which describes how well all of them are aligned to each other. And so we'll talk about what the challenges are there and different ways you can go about quantifying that. Then things like self-avoidance. And so for people from sort of a chemistry background, this will be familiar to you in terms of sort of crystalline or quasi-crystalline structures, is that when you look at a crystal, it's very evident quickly sort of where the atoms are in this lattice and how they're organized. If you now take an image of something, trying to figure out what this lattice might be and how everything is organized is very difficult. And these are some of the tools that are available for doing that. And then finally, this more general idea, which is the two-point correlation function, which will then build off into texture analysis. So if we look at sort of the metrics that we have, there's a number which are point operations. And so that means you've basically transformed your image into a list of points that you're interested in. And so when we did the shape analysis, that was this kind of analysis. So instead of having just a bucket of voxels, you now have a center of mass or a center of gravity, a volume, an area, and all of these other pieces of information associated with a single point. And so the kinds of analyses we can do with that are this nearest neighbor, Delanoy triangulation, distribution tensor, tessellation, alignment. Those are all the things that make sense for sort of looking at single points. The other types of operations that we have are then voxel operations. And so this is when we still have an image as voxels, and we want to do some more analysis on that. And so that's where Voronoi tessellation also comes in. Neighbor counting, so how many neighbors are you actually in contact with? And then two or endpoint correlation functions. And so when we look at kind of what we start with, we have our original cell image that we've kind of always used as an example in this course. We've gotten rid of noise, we found the shapes, we've even separated sort of joint cells with a watershed transformation. And so we can characterize all of these things. So we have, average volume, average orientation, average surface area, but that's not necessarily all the information we were looking for in this sample. And so when we take this image, if you want to know how many cells are alive in this question, this image has no staining of cells being alive or not. Obviously, if it had some kind of staining, that would be much easier. You just measure how bright or how blue or how yellow the cell is in order to measure if it's alive or not. But in absence of that, you could have a hypothesis like maybe small cells are dead and larger cells are alive. And so if that were your hypothesis, you could simply look at the volume of all the cells, which we've already calculated, and see which groups they fall off into. If the question were maybe living cells are round and dead cells are very spiky and pointy, then we could potentially look at anisotropy or these ellipsoidal models, and that would begin to tell us more about if these cells were alive or dead. And now if we sort of say, okay, both of those approaches aren't working well, but we know that cells that are alive are the ones that are packed closely together in groups, and the cells that are dead are the ones that aren't. We haven't really covered any techniques that would help us do that. So does anyone have any ideas about how you would try to measure something like that? I mean, if you look at an image, it's very easy to say these cells are packed together closer than these cells. But how could you go about measuring that? No ideas. The neighbors. Yeah. So you could use, if we stick with like sort of the pixel approach that we've done before, we have sort of these morphological operations or distance maps, and we could potentially grow those out and try to figure out how many other objects are around you. And so rather than just doing a neighborhood being 1 pixel away, you could have a neighborhood being 10, 20, 30 pixels away. And that would then give you some idea that these cells are very close and these cells are much further apart. Yeah, you can visually inspect the sample. You could examine the raw positions, but that doesn't really tell you very much. Then the next kind of step after, maybe looking beyond the neighbors, was you could make boxes. And so if you divide your image into little tiles like this, or maybe bigger tiles like this, you could then count how many cells are inside each one of these tiles. So here you have 2. Here you have 2 as well, but here you have, 6 or 7. And then here, many more. And so by making little boxes, you could then color each one of these boxes by how many cells were inside it. And that would give you an idea of what that density was. Yeah, and so if you want to know what cells, how the cells are, sorry, that was the last cell. Yeah, so we had a few more. And so now if we want to compare 2 regions in the same sample or even 2 different samples, this box method then becomes a little bit tedious because now you're drawing boxes for each one of these regions and you're counting how many cells are inside it, but you see if you shift this box a little bit this way, now there's only 1 cell inside, and if you shift it a little bit this way, then there's now 3 cells inside. And so it's potentially a quite variable metric for cell density because based on exactly where you put the box, you might get a slightly different result. And so now if we start to look at other questions like how could these cells be communicating, if they're physically connected, as is often the case with like neurons, then it's quite easy to do this. We have this watershed analysis where we have 2 or 3 bodies that are grouped together, and watershed will help us take them apart. So that works quite well. If they're not physically touching, but let's say if they're oriented in the same direction, then they're probably communicating because they're feeling the same sort of forces or responding to the same chemical gradients. Then you have this kind of problem of average orientation. So, if you have an angle between 0 and 360 degrees, and you take the average of 0 and the average of 360, then you end up with 180. And so the average of 2 cells pointing upwards is a cell pointing downwards, or the average of a cell pointing up and a cell pointing down is a cell pointing to the right. And so that may not be the best approach because you end up with averages that don't really make sense when you're working in an angle space. Maybe you could say cells that are close enough are communicating. How would you quantify that? And then if you come up with sort of further ideas of maybe the cells kind of form a hub and spoke network inside of your sample, then how would you answer that? And so these are kind of the questions that we're aiming to come up with tools for so that we can answer them in fairly straightforward ways. And so now if we want to know how the cells are being nourished, maybe closely packed cells are better nourished. We have this counting the cells in the box. And then maybe cells that are oriented around other structures like blood vessels or something else in the sample are being nourished by them. And so we can look at, are they oriented around this? How far are they distributed away from these structures? And what sort of tools do we need to quantify this? And so the example here is all biological, but this applies to material science as well as it does to biology. And so if you're looking at pores inside of magma or liquid foams, you have similar sorts of problems and similar questions that you're trying to answer. And actually most of these tools that we're using come from the material science world and have been adapted to these sort of biology problems. But they're built on sort of the physical models that you have in material science. And so when we look at kind of what would we still need to be able to do, is we want to have a way for counting cells in a region and estimating things like density without having to draw arbitrary boxes or make sort of arbitrarily large erosion or dilation operations. We want to find out how many cells are near a given cell. So like, what are the neighbors of a cell? How do we define that? And how can we do something meaningful with it? And it'd be good to quantify how far apart cells are and then compare different regions within a sample or even different samples to each other so that we can start to measure those sorts of things. And it's clear that we also need a way for quantifying and comparing orientation, because you have a number that comes out, but taking the average or the mean or the standard deviation of this number doesn't really help us. And so we want something else to do with it. And then if we look at kind of what would be really great, would be to have some more generic tools that could handle a large variety of different problems. And so, you can see here, this is a very limited set of questions that you might possibly have. But when you're dealing with complicated structures that have multiple phases, multiple different types of structures, and you're interested in how they're interacting, it would be good to have tools that are really able to be adapted to those kinds of problems, and that's what we'll cover at the very end of this. So, one of the reasons why these things are quite important is because the measurement itself often is affecting the sample. And so even measurements like X-ray tomography, which claim to be non-destructive, are still changing your sample. If you take your sample out of water, let it dry out, make a measurement, and then put it back in water, it's potentially very different than it looked before. If you're dealing with even higher resolution techniques where you're at sort of the nanometer scale, then you are very frequently completely destroying your sample. And so even when you're able to make measurements of the same sample, it can be quite difficult to register and match these samples together. And so what we want to have here are tools where we can analyze samples that were measured at different time points and somehow be able to compare them in a meaningful manner, where we don't necessarily have to say this pixel maps exactly to that pixel, but we can say these two samples we expect to be similar, and these are the differences that we're able to observe. And so what we want to have is we want to have sort of a number of common transformations, and we want to have metrics that are able to actually measure well what happened to this transformation. And so what we would like to be able to say is sample B after a certain treatment looks like sample A stretched to be 2 times larger. Or, so if sample B was bone from a certain mouse, and sample A was a bone from sort of the parent strain of this mouse, and you knock out a gene, you want to be able to say, clearly the bones are not identical. We don't expect to be able to match up points in one bone to another bone. But when we look at the structures inside it, it looks like B is a stretched out version of A. And so as a qualitative assessment, that's very easy to make. But as a quantitative analysis, this is very difficult to do. And so this is sort of the basis for what we're going to do with these tools, is try to figure out how we can quantify those kinds of analyses. And so now what we have is we sort of have a small region of the cell sample. We've analyzed where all the cells are. So we have the X, the Y, and the orientation for each one of these different cells in our sample. We can then start to analyze it. And so we can take X, Y, length, Vx, Vy, theta, and we can do a full statistical analysis where we see what is the minimum, the quartile, the median, the mean, the maximum, everything else. And this gives us certainly lots of information about the objects that we have, but none of these answer kind of those questions we initially posed. Some of them might be getting closer to that, but in the form they are now, none of them are a direct answer to one of these questions. They're all just sort of the statistical analysis of data we've collected before. And so what we want to have is something more meaningful that we can extract from this table. And so simple statistics, if we're looking at orientation, which is what I had just mentioned before, you sort of have the mean of 0 and 180 is equal to 90. And the distance between minus 180 and 179 is 359 degrees. But in fact, we know that neither of these things are really true. You know, that doesn't represent the average angle because you actually have nothing pointing that direction. And the distance between minus 80 and 179 being 359 isn't really true because you have one that's pointing down this way and one that's pointing down this way. They're 1 degree apart, or not 359 degrees apart. And since when we look at the analyses that we have, we've never really defined a head or a tip. So if we go back to this image of these cells, we have an orientation that we calculate from this ellipsoidal analysis or this shape tensor, but we've actually never said which way's up. So for our analysis, a vector going this way is exactly the same as a vector going that way. Which means that if we're looking at 0 and 180 degrees, the mean is 0, or the mean is 180, because we haven't said which way is up, and so they're the exact same angle that you're measuring inside of them. And, you know, means are not commonly very useful anyways. And so here's an example of sort of a healthy and a sick group where you measure the distribution and try to show the mean, and you don't see very clear distinctions between those groups. Density is sort of a similar problem where, you know, how many objects are in a given region or volume. And the naive or very easy way to calculate this is by just taking the number of objects and dividing by the volume. And so you have n objects in x unit of volume, and you just divide them. And so here we have 10, 100, and 1,000, and we see that that matches very well with our intuitive understanding of what density should be. We unfortunately have a problem where there's now a lot of different samples which have exactly the same number of points per volume, but look for us very, very different. And so here, all of these have 500 objects per square millimeter, but the distributions in all of these is very different. And so all of them in this simple density metric would get exactly the same value, which is probably not what we want to have, because for us it's very evident that this density is different than this density, and that this density is very clearly different than that density. And so if we're trying to quantify differences between these samples, we don't necessarily want a tool that's so easily fooled or groups all of those things into the same distribution. The last sort of tool that we'll introduce right now is this idea of neighbors. And so, you know, be situated next to or very near to another object. And as we see, the definition does not sound particularly scientific, and it isn't. You know, how close is very near? Does it actually have to be touching? Does it have to be closer than any other object? Is there a certain fixed distance? Is, you know, half the size of the object, or 10 millimeters? Or there's a lot of potentially different ways of doing this. And so, given a set of objects with centroids at P is x vector 0, x1, x2 through xi, we can define a nearest neighbor very easily. And so the nearest neighbor is simply the other object in your list that's closest to your current point. And so that's, you know, not difficult to define because there is only one object, or usually only one object that's the nearest, and if there are multiple, then you just randomly pick one. You can then define a nearest neighbor distance and a nearest neighbor angle. And so the nearest neighbor distance would be then the distance to this object, and the nearest neighbor angle would be the angle of the vector pointing to that object. And so now if we look at what this nearest neighbor definition actually looks like, we have a grid of points here. All of them have a different label between sort of 1 and 80, I guess. And these lines in the image show where the nearest neighbor is. And so for this red point here, the nearest neighbor is this orange point there. For this orange point, the nearest neighbor could be this one, but happens to be this one because there's not a very clearly defined way of dealing with points that are exactly the same distance away from each other. But we see that the nearest neighbor distance is fairly consistent, whether it's going to the left or to the right. Yeah, and this is why we have this additional clause where if there's multiple equidistant neighbor, nearest is chosen randomly. And so this is kind of the image we get when we do this nearest neighbor analysis on our data. And so what we want to have now is a way of showing what all these metrics mean. And so what we do here is rather than taking a real sample, we start off with a completely synthetic sample. And so we have a completely synthetic sample, and we apply a number of different transformations to it. So the first transformation we apply is compression, and this involves scaling by an alpha component in every direction. So this is very simple. You know, if you scale by alpha, and alpha is less than 1, you compress it. If it's greater than 1, you expand it. Shearing is then very similar, but this is where you then have a slightly different effect as you go further down in the sample. And so as you increase in y, your x position gets shifted. So it looks sort of like a shear. Stretching, and this is sort of a nonlinear transformation of your system so that you move objects away from each other based on how far out they are in your system. And then the last one is sort of a swirl, which is a transformation that just kind of rotates points around so that you get a nice view of them. These transformations themselves are not important at all. It's just the idea of how can we create a system that we manually make changes to so that you can understand what the parameters actually mean. And so here we have the positions and neighbors for a system under 3 different compressions. And so this one is where your alpha is 0.8, so all your points are closer together. This one is where your alpha is 1, and so it's this sort of default case. And this is one where you stretch them out. And so how would you expect nearest neighbor to change with this system? Yeah. Yeah. But if we look at like the nearest neighbor distance, how would we expect that to change as we change alpha? So it's the same in both. So the stretch that we do is just this alpha x, alpha y. Yeah. So the nearest neighbor distance gets stretched as well. And so here it's fairly easy. I mean, you wouldn't need these tools to actually say this sample looks compressed, this one looks stretched. But what the nearest neighbor distance tells us is kind of how stretched or compressed it is. And so this distance will change linearly with alpha. And so as you increase or decrease that value, you can now measure that very easily by looking at the nearest neighbor distances. Yeah? Here, well here x and y.
If you move x, y, it's 2, you move x, x, 2 as well. Like a diagonal, this is 4 and this is 2.
Yeah.
You take that into account with the nearest neighbor?
Well, so the nearest neighbor only gets you the nearest one. Yeah. So we have no diagonals on here. You only have one length unit because there's always one that's very close. So we'll see in the shearing example here. Actually, no, we don't. I thought we would. You'll see in other examples where it will do a diagonal. Like there's no restriction. It just finds the closest point. And in a grid, the nearest, if the spacing here was 1, then it's 1 over and 1 up are equally distant, but the diagonal one is 1.4. So it will never pick the diagonal one as long as there is one to the right and one above. So it's not, So it's not like a one-to-one mapping. So there can be 20 points that have the same nearest neighbor, which is like 1 point in the middle. It's not like once it's a nearest neighbor for 1 point, it's taken up and another point has to choose another one. And none of these points for the nearest neighbors have 2 jumps. It's always the closest point. The only thing that's sort of random is if it's up or left or right or down, because it's a grid and so all of those distances are the same. So now we can see, if we look at this image here and we measure the nearest neighbor distances, it's quite nice. We can make a histogram and we see that there's the ones that have the stretch factor of 0.8, all are exactly here. The ones that have the stretch factor of 1 are all exactly here, and the one the stretch factor here are 1.2. And so the nearest neighbor distance scales perfectly linearly with this stretch factor, which makes our job very easy. If we wanted to measure the stretch factor, all we need to do is measure the nearest neighbor distance, so the average nearest neighbor distance, and that will tell us the stretch factor immediately. Whereas if we had this list of points to try to say how compressed this is compared to this, you would have to go through every point here and be, where does this point match up in that image? And that's a very difficult, time-consuming task. And if you make a mistake about matching one of those points up, you can have a huge problem, a huge artifact in your match. And with the nearest neighbor distance, we just measure that for all of the samples, and we can then say, this sample is more compressed than this sample. And because the distributions are so perfect, because it's a grid, it's very easy for us to show that we now have, there's no possible overlap between these two images at all. We can then look at the orientations because we measure that angle as well. And here, as sort of we expect, you don't see any differences. So it's randomly oriented, and it's just as randomly oriented independent of this stretching factor. So now if we take shearing, which is a slightly more complicated analysis, we have kind of our default sample here, which is 0, which looks exactly like it did before. And now we can shear it a little bit. So we shear it with this alpha factor of 0.5. And all that does is it kind of moves each layer a little bit over the further down you get. And so what's quite interesting is that you see all of a sudden after this tiny shear, there's now no more vertical lines in this image. So all of the nearest neighbors are the points immediately to the right or to the left. There's no points which are up and down anymore because this distance is now larger than this distance, and so we'll always use that distance. Once you shear it enough, you now get to the point where you're matching up again. So there's points that are directly above and below, and so you start to get those angles again. And this shows us kind of the distribution of nearest neighbors. So these are all those little vectors that we have in the image. And here it's pretty isotropic. Here it's now perfectly along this axis. There's absolutely nothing in these up or down axes. And then here it's back to being isotropic again. And so when we measure that or quantify that, we see that the nearest neighbor distance is exactly the same. So doing the shear did not change the nearest neighbor distance at all. We can't measure that with a nearest neighbor distance. But when we look at the orientations, we see major differences there. And so when there's this shear of 0.5, all of a sudden none of the sort of angles here come in at all. And it's very clearly measurable that that's happened. Yeah.
Like the graph, yeah.
Yeah. So those graphs are basically if you take all of these little arrows and you put them on top of each other.
Okay.
So you move them all to the center of the axis so that the bottom of the arrow is right here. Then you can see where all the arrows are. So rather than having the arrows in this image, where they're centered at a point and going up and going to the right and going up, you have them all centered here. And then this curve shows sort of a contour map at how frequently is the tip in each one of these positions. Yeah, it's sort of a confusing plot, particularly when everything's all the same, that there's not much interest. But we'll get more exciting systems there. So now this is the stretch system that I mentioned before. And so this is the default state where everything's evenly distributed. This is now where you sort of stretch things towards the edges. And so that makes points that are closer to the edge even closer to them. It's sort of a simple mathematical transform. And this is then where things get pulled towards the center. And so basically the idea here is that we make systems where we artificially induce a change so that we can show which of the tools that we've developed are able to measure that change well. And so here we have that exact graph we had before, where in the normal system we have sort of the up, down, left, right, very clearly visible, equally likely in every direction. And now we see that the stretch system starts to get different lengths. And so the point here in the middle is much further from all the other points than the points near the edges. The points near the edges get closer together, and the closer you get to the middle, the further away you get from your neighbors. And then here we have the exact opposite effect taking place, where here the points in the middle get much more densely packed, and the points at the edges get much more sparsely packed. And so that's sort of the graphical representation of all of these nearest neighbors. Yeah.
The lines? What are the lines? No, yeah.
The lines.
Yeah, the lines.
The red.
Yeah.
Yeah, so the red lines are sort of a contour map on the probability that a point's tip is in that region. So because all of the point tips are here, 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 and here, you get maps that are just, this is the highest density for that.
Oh. And what are the, yeah,
This one.
Yeah.
So this one you don't see the maps very well. You see the little red dots there, but because they're so spread out, that map becomes much less clear.
Oh, so those are the density. Like the
Yeah.
probability.
Yeah. Yeah. Why would you do this? Yeah, so the idea for this is that we have sort of this collection of tools that we've collected where you have nearest neighbor distance, where you have density, you have this angle, what are the other ones we have? And we need to know how these tools are useful. And so when you calculate a Voronoi tessellation on your image, it will give you some result. But if you don't have some framework for interpreting this result, it will be very difficult to say what that means. And so here what we do is we've introduced a set of things that we know that are very easy, like compression, shearing, stretching, swirling, and we show how they affect a system that is very simple that we understand, and what changes in the parameters that we have afterwards are.
But would you apply these stretches to your actual samples, or is it just to validate and see the change?
It's just to validate and see the changes. You could potentially apply these to your actual samples to sort of test a hypothesis that you have. But for, I guess, the backward going perspective would be, you have a sample, you've measured a bunch of cells or pores inside of your sample, and you want to be able to say, or you then measure the nearest neighbor distance for these pores. In the sample that you heated up to 200 degrees, the nearest neighbor distance is 5. And in the sample that you've heated up to 300 degrees, the nearest neighbor distance is now 4. What does that mean? You know, you could write a paper and you could say the nearest neighbor distance is 4, and then we heated it up to 300 degrees and now it's 5. But in terms of what that actually meant for changes in your sample, it's sort of difficult to say. And so what we do here is we apply a number of transformations to show what that looks like in a parameter like nearest neighbor distance. So that we see here, if you had a sample where you measured 0.8 and you had a sample where you measured 1.2, and you saw that the orientation of the nearest neighbors was the same, and the only thing that changed was the distance, that probably means there was some kind of compression going on in your sample. And your guess would be that it's probably a hydrostatic compression, so in every direction equally, because your distribution didn't change very much. And so the idea for this is really to be able to interpret when these changes happen, what they mean. Right. So that if you saw all of a sudden in a crystalline structure that the angles of the nearest neighbor distance changed significantly. So it went from being equal in every direction to being just to the left and the right. You would assume there's some sort of shearing process going on. There's something that's causing changes to happen sort of along this y-axis that aren't happening along the x-axis. Or of course, it can happen in the other way as well, where, you know, if you were to shear in the other direction where these slices then go further down, then you would see this curve rotated, or these rotated by 90, where they're all then up and down and there's nothing to the left and to the right. And so the whole idea of this is to really have a feeling for what these metrics are trying to quantify so that you can do some analysis yourself. And so if we look at kind of sort of a more concrete example from like the exercises. Just to justify it a little bit. That what we'll have in the exercises is you'll have like a sample A and a sample B, and your goal will be to show what's the difference and what's the possible explanation if they came from the same original sample. So if you had a sample A measured it under one circumstance and a sample B under another circumstance, how could you quantify the differences there? And based on these different quantities, how could you then say what happened? Similarly with, you know, finding layers in a sample. If you have a sample, you look at this, it's very clear where those layers are. No one would doubt for a second that there's a layered structure there. But that doesn't mean it's trivial to find those layers automatically. And so this would be about how do you apply those tools to do that well, and particularly when the layers sort of aren't along a clear axis and the points are sort of randomly distributed, how can you come up with some analysis that measures that well? Or here, for example, where all of the layers are just affected by spacing. So how could you come up with a way for measuring those different layers and grouping those objects out when it's just the spacing between them that's being changed? And so the whole idea for these kind of exercises or these kind of examples is to see what this actually does on very simple systems. And so we see for the shear distribution, the length doesn't change at all. We get a change in distribution. For the stretch system, we then get changes in the width of the nearest neighbor distance. And so we go from our unstretched example, so this one where everything's evenly spaced, where you have a nice curve in the middle, where sort of all the points are exactly one distance away from each other, to a wider and wider distribution as you stretch that more and more. And so what that means for sort of the interpretation perspective is that, if you had a very crystalline, evenly spaced structure, that nearest neighbor distance would be a sort of very narrow peak at a certain value. And the more inhomogeneous or unhomogeneous your system is, or heterogeneous your system is, the wider this distribution will get. And so this gives you sort of a way for interpreting, okay, if you have a very, very broad nearest neighbor distant distribution, then your sample is very heterogeneous. And that means that things are spread out a lot. And so now you could have a base idea for what might be going on in your system and what tools you could use to quantify that well. Whereas we see with the shear direction, the orientation does not really change at all. And so the distance gets broader. The mean doesn't really shift very much. So here the mean might shift a little bit to the left. But for the most part, that stays the same. And so measuring the mean nearest neighbor distance wouldn't help you much. But measuring the standard deviation of the nearest neighbor distance would tell you something about it. So now the last system is kind of the swirl system, where you have, 0 swirl is your standard system, 4 starts to swirl it a little bit, and then 18 starts to swirl it a lot. And so swirl is obviously not a real transformation. This doesn't come from material science or mechanics. This is just an example of a slightly more complicated analysis that you could have. And then we see when you look at the nearest neighbor orientations and distances that your 0 looks like this. You have equally numbered up, down, left, right. And as you start to swirl it, you start to get more and more kind of off-axis ones. And as soon as you've swirled it enough, it's now pretty much a completely random distribution. So it's in every possible direction, and it's about even in every direction. There's no more sort of resemblance of what you had at the very beginning. And so when you look for the statistics of this, you then see sort of with your 0 swirl system, you had everything in one peak. So everything was at 1.0. And as you start to swirl it more and more, this gets broader and broader and shifts down. You then see that the orientations change as well. And so in our 0 system, you had very narrow peaks at 0, 90, 270, and 180 and 270. And as you start to swirl it more, these peaks shift and get broader and broader. And so that would be sort of a starting point for analyzing these kinds of systems, where you could then see what are these peaks and how much are they changing. So what we see with these systems is the orientation appears to be somewhat useful, but because we're dealing with a grid, it's very random. And, we shouldn't potentially be using such perfectly grid systems for our examples, because as we saw, a tiny change could have a big effect by making things much further apart than they would be before. It's then some of the criteria are quite difficult. So as we kind of measure the mean nearest neighbor distance, that's very easy. The standard deviation is also very easy. But with like this last example where we had these peaks, how can you measure how wide this peak is not trivial. Because it isn't one distribution, it's sort of 4 different peaks, and measuring the width of 4 peaks is not an easy task to do. And so, how would you fit a curve and then measure the width or do something else? And so that's not something we'll deal with at the moment, but it's why we don't work with grid systems normally. And so a uniform grid of points kind of strongly influences the results, what we can take now is sort of a random grid of points. And this is where it starts to become much more sample specific. And so here we just take a random distribution, but often you know a lot more about your random distribution that you can use to make a random synthetic system that you can start to analyze with these tools. And so I think we'll take a short break here, unless there's any questions on that first part. So it's a little difficult to get your head around some of these ideas at first. This is all stuff that won't be, you don't have to know what a swirl is or how swirls work, but you should be aware of, what compressing a system would do to your nearest neighbor distance, or what a shear would do to your nearest neighbor distance, and sort of have a feeling for how these metrics apply to real systems. I mean, that's the main point of this, is that you have a way of understanding that, and that we're going to introduce a lot more tools for analyzing this, and knowing how they actually apply to systems is very important, because they're not always completely intuitive what they're extracting. So, okay, we'll have a short break.